Hey there, chemistry. I want to talk to you today a little bit more about conversions, but extending it from what we've been doing. So basically, we have been doing one-step conversions. We've been doing conversions that only take one conversion factor, right? But that's not the limit of what you can do. You can do a whole bunch of conversions, and that's the beauty of dimensional analysis, is even if you have a whole bunch of relationships, you can string them all together. Even if your units are made up, you can still do dimensional analysis. Even if your units are things you're not familiar with, you can still do dimensional analysis and complete your conversion from one unit to the next unit. So I want to talk to you about that today. First of all, let's talk about if you have a unit that's completely made up, right? So let's talk about if you have we'll go My Little Pony inspired here. Okay, we're gonna have a relationship between heartsease. Oh, that was a really long word. Let's pick a shorter word. And flanks, because the ponies all have their little symbols on their flanks, right? Okay, so let's say that there are 3 heartsease on each pony's flanks. All right, if you are not a My Little Pony fan, what we're looking at is something to the effect of, they have their little pony legs, right? Their little ponytail. Can you tell that I have young children at home who may or may not love My Little Pony? All right, there you go. There's 3 heartsease per flanks. Now, you may have never heard of a heartsea if you have never hung out with my children, but of course, they exist. Of course they do. You just haven't heard of them. Oh, that was a scary pony eye. I don't know if the eyelashes make it any better. Anyway, moving on. So I just totally made this up, right? And if I have 750 flanks, I want to know how many heartsease I have. Now, this is the beauty of dimensional analysis, is you don't need to understand what you're talking about here, because we can solve this just with our units. Whatever unit is on top automatically goes on the bottom. We're trying to get out of that unit of flanks. Okay, now I have a relationship here. So in my relationship, flanks are related to heartsease. I'm going to, I guess I'll just spell the whole word out, right? Okay, so we have my measured amount of 750 flanks. Now, notice that number does not come from my relationship. That initial number is measured or given to you in the problem. That relationship that you see, that's always true between heartsease and flanks, is here in the middle. So I set up my units completely. I know that flanks will reduce out. I'm going to be left with heartsease. I'll abbreviate it there. And it's going to be 3 heartsease per 1 flank. So all I do here now on my calculator is I'm going to take my numbers, 750 times 3 divided by 1, and I'm going to get my answer, which is going to be 2,250 heartsease. So this is the beauty of dimensional analysis. You don't have to understand the concept, right? You don't even have to know what your units stand for, as long as you know that one unit on top of the other unit are going to reduce out, and this must be a relationship between the two. Now we can take this concept and keep running with it in terms of chemistry concepts. So here we have something, it wants me to calculate the volume in liters of 750 grams of helium atoms. Now, I'm going to set it up the exact same way, 7,500 grams of helium atoms. Grams is going to go on the bottom. Now, I know that ultimately I want atoms, and here's why conversion problems that take multiple conversion factors are a little bit trickier. You have to know that there is no direct relationship between grams and liters. Now, something that will really help you is memorizing your conversion factors in chemistry, right? We've talked about that before. The other thing that can really help you are your flashcards. If you have your bundle of flashcards, you can look through them and say, do I have a relationship between grams and liters? The third thing that can really help you is this stoichiometry chart down here that organizes some of your conversion factors for you. And the way this is going to help is you can circle where you're starting. We're going to start with grams of helium, and we want to end in liters of helium. So notice I'm going to stay on this side of the chart. If A is helium, then I don't need any of these, because I'm never going to go out of anything but helium, right? So I'm going to start in grams of helium. I'm going to end in liters of helium. So notice here, this is going to help you set up your problem. The first thing you have to do is go to moles. We have a relationship between grams and moles. It's molar mass, right? There's no relationship directly between grams and liters. So the first thing I have to go to is moles of helium. And then I continue on, times a line. The unit that's on the top automatically goes on the bottom, moles of helium. Now I do have a connection or a relationship between moles of helium and liters of helium. So I can put liters of helium right there. Once I have set the problem up in units, now I'm going to go back and plug in numbers. So what is that relationship between grams and moles? Well, it's molar mass, and we find molar mass on the periodic table. So helium's molar mass is 4.003. So I'm just going to keep 3 significant figures, 4.00 grams per 1 mole of helium. That is the relationship between grams and moles that we find on the periodic table, called molar mass. And liters per mole of a gas is going to be 22.4 liters per 1 mole of the gas at STP, which we are. We're at STP. So we just use dimensional analysis to set up 2 conversion factors. And then we take our calculator. We're going to multiply across the top, multiply across the bottom, and then divide the top by the bottom. So 7,500 times 22.4 times 1 divided by 4 times 1, which is 4. So my answer is 42,000 atoms. Oh, liters, sorry, not atoms. I was like, that doesn't sound right. Liters of helium. Okay, and I can double check. Did I set it up right? Grams and grams, moles and moles. I'm left with liters of helium. I did set it up right. I can be confident in that. All right, let's try another one. This one involves a reaction. Notice we're given a reaction at the top. Okay, so let's look at what they ask us and what they give us. So what mass of oxygen will be needed to burn 36.1 grams of B2H6? So notice I'm going between 2 compounds. So I'm going to have to go from one side of this little graph to the other side of this little graph. We'll say oxygen is going to be A, And then B2H6 is going to be B. Okay, so let's set up what we do know. 36.1 grams of B2H6. I know I start there. And I know I want grams of oxygen in the end. So without doing anything else, this is the information that comes straight from the question. This is the first step. If you get stuck on these problems, this should be the first step you're trying to do. Can you set up what you have, what's measured, right? You're given, and the thing you're trying to find. Can you set that up? Step 2 is setting this up through the units. So let's go ahead and fill in all the units here. Grams of B2H6 will go on the bottom. Now, if I'm in grams of B2H6, there's only one thing I can get to. Oops, I'm backwards. That's not grams of B2H6. Let me circle it in the right place on the graph. Okay, grams of B2H6 would be here. There's only one place I can get to. The only thing I can get to is moles of that same thing. So the top of my fraction must be moles of B2H6. Remember, if there's no line connecting it, you don't have a relationship there, unless it's not on this chart, and then that's a different discussion. All right, so is this what I want, moles of B2H6? Nope, it is not, so I need another fraction. The unit on top automatically goes on the bottom, moles of B2H6. Now I can get to lots of things. I can get to particles, back to grams, I can get to liters of gas, or I can get to something new. What do we want to get to? We want to get to oxygen, which is something new. So I'm going to cross the mole hole here and go to moles of A. So moles of oxygen. Now, is that what I want? No, it's closer. Still not what I want. I want the mass of oxygen, not the moles of oxygen. So times a line. Whatever unit's on the top also goes on the bottom. Moles of O2. Now from moles of oxygen, again, I can get lots of places. I could get back to B2H6. I could get to molecules of oxygen, grams of oxygen, or liters of oxygen. Where do I want to go? I want to go to grams of oxygen. So I'm going to need, right? Grams, yes. So I can get directly there, grams of oxygen. So I've just set up my problem using units only. So now let's go in and plug in numbers. This first conversion factor is going to be the molar mass of B2H6. So let's figure out what that is. So 6 hydrogens and 2 borons. Okay, so using 3 sig figs, I got 27.6 grams per 1 mole. Now the mole to mole ratio here is going to come from the coefficients of the balanced equation. So what are the coefficients of B2H6 to oxygen? Well, in this reaction, it's a 1-to-1. So 1 mole of oxygen to 1 mole of B2H6. And then my last conversion factor is moles to grams for oxygen. So again, we need the molar mass, 2 oxygens. That's going to be 32 grams per 1 mole. Okay, my problem is set up. So now let's double check that we've set it up correctly. Do all my units reduce? Grams B2H6, grams B2H6, moles B2H6, moles B2H6, moles of oxygen, and I'm left with the unit that I want in the end. There's a pretty good chance that I set this up correctly. The only way now I could have made a mistake is if I use the wrong conversion factors or I put the numbers in the wrong spot. So I can go through and look, is this reasonable? 27.6 grams per 1 mole. That sounds reasonable. 1-to-1, yep, that's what my reaction says. And then 32 grams per 1 mole, that also sounds reasonable. So now I'm going to go through with my calculator, multiply across the top, divide by everything on the bottom. So 36.1 times 1 times 1 times 32 divided by 27.6 divided by 1 divided by 1. And my answer is going to be 41.9 grams of oxygen. Is this a reasonable number? Yeah, it is. The masses of these two things are fairly similar, 27.6 to 32. So that won't cause a huge difference in the masses. And my ratio is 1 to 1 between them. So that's a pretty reasonable answer. And I have set up a dimensional analysis problem that has more than one fraction. So until you get comfortable with this, use your chart, use your flashcards. Eventually, you're going to memorize which conversion factors exist and which don't, which ones are real relationships and which are not. That's something that is really important to figuring out how to do these conversions between one unit and another unit. All right, so let me know what questions you have. We will practice this together. I will see you in class.